This is the first of several videos about intermolecular forces. And the three main types of intermolecular forces are dispersion forces, dipole interactions, and hydrogen bonding. So these are the forces that determine the state that something is in. So let's talk about what the three states of matter are first. So we've got solid, liquid, and gas are our three states of matter. You know and love them, and you can identify them. Solids have a regular structure. The particles are very close together, and they aren't moving very much. They're fairly stable, fairly stationary. Liquids, the particles are a little bit farther apart. They take the shape of their container. They move around and past each other, and they're wiggling around and moving a little bit in their container. And gases are very far apart in their container. They're moving very quickly, and they fill the entire container space that they're put in. And so what determines the phase a particular compound is in is what I like to call the push force and the pull force. So the push force trends in this direction. The push force is kinetic energy. And kinetic energy is how fast something is moving, how much thermal energy it has. And we talked about this a lot in the gas law chapter at the very beginning. The gases have the most kinetic energy, they're moving the most quickly, and that's why they end up in this phase. Push force pushes the substance towards the other side, towards the solid side. And these are the intermolecular forces, specifically intermolecular attractive forces. And those intermolecular forces hold the molecules tightly together. And this is what enables solids and liquids, these condensed phases, to even exist, is they're attracted to each other and they have low kinetic energy. So let's talk a little bit more about these intermolecular forces, what they are and what they aren't. So these are intermolecular forces. And these are interactions between different molecules. Okay, so the emphasis there is on between or intermolecular. So to give an example to help you remember, the internet connects computers, that is what this is supposed to be a picture of, computers in one place to a computer in another place that's far away. So the internet. The opposite of intermolecular forces would be intramolecular forces. We'll give that a lowercase I, we care less about those. And intramolecular forces are actual bonds. They're interactions within molecules, between atoms of the same molecule. So intra is within. So if we had the intranet is like the Lorentz internet. It's like accessing the shared drive, how you can only access it if you're inside of the Lorentz bubble. You have to be inside of the same bubble to get to it because it is the intranet. So we really care about the intermolecular forces in this chapter. It's the force that holds multiple molecules of a substance together. So there are three major types of intermolecular forces listed in the outline above. And those intermolecular forces have a more formal name, which is van der Waals forces, just in case you're looking for other literature about them. Okay. So the first type is called dispersion forces, and they have another name. They're also called London forces. Might have heard them called that. Second type is called dipole interactions. And the third type is called hydrogen bonding. It is important to note these are not actual bonds. So they're interactions. It's just called bonding because it's a very strong interaction, but they are not, in fact, bonds. So if we were to rank these three types of intermolecular forces according to their strength, dispersion would be the weakest, and hydrogen bonding would be the strongest. So the weakest would be up here, the dipole in the middle, and hydrogen bonding being the strongest intermolecular force. But it's important to note that if we were to put actual bonds, intramolecular forces on this scale, it would be way, 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 way off the chart down here. Molecular bonding would be way down here. So if molecular bonding was 100% strongest possible bond, hydrogen bonding would be at 10%, dipole forces would be at 5%, and dispersion would be at 2%. So hydrogen bonding is the strongest type of intermolecular forces, but it's nowhere near as strong as an actual bond. So these are much weaker than true bonds. Okay, so those are the three types of forces. So now let's dig in a little bit deeper and talk about the first one, dispersion forces, which is important because it affects all molecules, even those that aren't very special. Okay, so dispersion is the first type. These are the weakest of all of the forces. This type of force is present in all molecules. So whether you are a molecule that particularly likes to bond with other things, or if you're a noble gas that doesn't like to bond with anything, everything has these forces. Dispersion forces are also the force that holds condensed phases together. And when I say condensed phases, I mean liquids and solids, non-gas phases. So this is the reason that liquids and solids of things like the noble gases can exist. We have liquid helium at very, very cold temperatures. This is the reason that helium is able to reach a liquid phase. So we want to talk about dispersion forces. We need to talk about atoms. So when you have an atom, you have a very small, very dense, very positively charged nucleus in the center, and then you have a cloud of electrons around the outside. And most of the time, roughly speaking, they are fairly equally distributed. No part of the electron cloud is more densely charged than another part. And here's another one, because these are intermolecular forces, so we need to have at least two molecules. So this atom is the nucleus in the center, and the electron cloud around the outside, where we're statistically most likely to expect to find electrons. Okay, so what happens is that the electron cloud is full of individual electrons, and each of those individual electrons is moving about on its merry way, randomly in a straight motion, just like we talked about in the gas law chapter. But sometimes, instead of being evenly distributed just for a fraction of a second, more than half of the electrons end up on one side of the molecule. So instead of having a nice evenly distributed circle, we'd have something that looks like this, where more of the electrons are on one side and less of them are on the other side. And as we talked about in the refresher Lewis structure and polarity video, we can draw, this is called a dipole, when one side of the molecule is more negatively charged than the other. And we can draw a dipole arrow with the arrow pointing toward the more negatively charged side and a little plus on the tail to indicate the more positively charged side. So this is called an instantaneous dipole. It only forms for just an instant. It's very short-lived. Okay, and then we have our other atom. It's still over here chilling, equally distributed, going on its merry way. So when we have an instantaneous dipole form, it's a short-lived phenomenon, but it exists long enough to have an effect on its neighbors. So when one atom forms an instantaneous dipole, the atom next to it can feel that, and this side of the molecule with the partial negative charge pushes electrons on the other atom away towards the far end, and it induces a similar instantaneous dipole and the atom next to it. So now this one dipole in one molecule became two dipoles, and this new one is called induced, an induced dipole. So we start out with no dipoles. For just an instant, we have an instantaneous dipole, and that instantaneous dipole induces a dipole and one next to it. And that's why another name for dispersion forces is called dipole-induced dipole forces, because of how it forms. And so this can happen to any atom in any molecule that exists. But there are several factors that affect the strength of these forces, because as you can imagine, they're not the same for everything. So one of the factors is something called polarizability, which is related to the size. So polarizability is roughly a description of how squishy your molecule is. It has a big cloud full of electrons in it, and we want to know how easy is it to distort the shape from perfectly spherical to unevenly spherical. How easy is it to do this? So let's take an example from the periodic table. Let's take two of the noble gases, neon and argon, with neon being the smaller and argon being larger. So here's neon. It's pretty small. And here's argon. Argon is pretty big. So neon is number 10. It has 10 electrons in its little sphere. And argon is number 18. So it has 18 electrons in its cloud. So its cloud is quite a bit bigger than argon. And so because argon has more electrons, it's easier to distort from perfectly spherical to this instantaneous dipole. It's easier to do because there's more electrons in this cloud. So we're going to say that neon is not very polarizable because it's so small, and argon is going to be very polarizable because it's so large. So we'll put in an arrow here. And so not very polarizable means that it's difficult to distort this shape. It's kind of like a pool ball. It's very small and very hard, and it absolutely does not squish at all. And if something does not squish, if it does not distort into an instantaneous dipole very easily, it's going to have weak dispersion forces. So the opposite will be true for argon. So this is very large, it's very polarizable, and so it's easy to distort. It's like a giant beach ball. You filled it up as much as you could with air, and now it's a little bit squishy, and you can shove your hand into it if you want to. So it's easy to distort, so it has strong dispersion forces. Okay, so that's one factor that affects dispersion forces. Another factor that affects it is the shape of the molecule. Because what we're looking for is we're looking for a lot of surface area contact between neighbors. The more contact they have, the more easily it is to induce a dipole. So let's take an example formula, C5H12, and let's draw a couple different isomers of that particular shape. So let's draw one here It has a tetrahedral connection. And if we were to describe this shape, we can see that there's a carbon in the center and branches all around the outside. It looks kind of like a circle. So we could say this shape is roughly spherical, sort of. And if we were to draw this a different way, and we connected all of the carbons in a row, like this, there we go. So there's the exact same formula, same molecular weight, but the shape in this case is more straight and long. So we could say this one was more of a linear shape. And the difference between these two, if you picture an intermolecular force, if you picture an identical molecule right next to it, if we had two of these really linear molecules right next to each other, there's a lot of surface area where they can contact each other because they're so long. So there's high surface area for a linear shape, and that means we're going to have high dispersion forces. Because the more surface area you have next to your neighbor, the more easy it is to induce that dipole in the neighbor. So the sphere, if we were to picture a sphere of equal size roughly next to it, there's not as much surface area here where they're in contact. They're not touching each other as much, so they're going to have weak dispersion. So the highest dispersion forces are very large, very polarizable molecules, and longer, more linear shapes. And so you say to yourself, how do you know this is true? You've drawn lots of pictures of molecules. How can you prove that these dispersion forces are actually the strongest? Well, dispersion forces have proof, and that proof is in how easy it is to change phase. So if you think about these dispersion forces and how they hold liquids and solids together, if those forces are weak, if they don't hold them together very easily, then as you add kinetic energy in our push from the previous picture, that push is going to easily push them apart. And it'll push them apart so much that it'll be able to jump into the gas phase. So our proof is in the boiling point, what temperature the boiling point is. So we could add a line to our table here, and we could say if something has weak dispersion forces, it's going to be easy to pull it apart. So the boiling point is going to be lower for this one than for the more polarizable one. And the same is true over here. If we have something that's more spherical and has weaker dispersion forces, it's going to be harder to hold it together. So it's going to jump into the gas phase more easily, and it'll have a lower boiling point than the one with the more linear structure. So that's everything you need to know about dispersion forces, and the next video we'll talk about dipole interaction.